Okay, so this week we're going to be looking at chemical equilibrium. And just to let you know, chemical equilibrium is really one of the very important topic in the AS and in the A-level chemistry in general. So pretty much he did some bits about the chemical equilibrium in the GCC. But the whole idea of the chemical equilibrium is that we're trying to tell you guys that we have two types of chemical reaction. We have what we call the reversible reaction, and we have something called the irreversible reaction. So let's just try to talk about this again. So in terms of the chemical reaction, we have two types of the chemical reactions. We have what we call the irreversible chemical reaction, and we have the reversible chemical reaction. So far in your studies, we've been mainly working with irreversible reaction. This is similar to the example that you did in the GCC. If you have the calcium carbonate and you heat it up, this is going to break down to calcium oxide and carbon dioxide. So this is what we called irreversible reaction, because these two cannot react again to form calcium carbonate. So the reaction is only in one direction. Okay, so this is pretty much similar to this silly example that we're showing here. So if you're actually cooking an egg, isn't it? You're gonna get the egg, you're gonna break it down, you made it, and you make the egg. So whatever changes happened, you cannot bring it back, and we call this a reversible reaction. What are the properties of the irreversible reaction? If you have an irreversible reaction, the reaction will be always going in one direction. So reactant reacting together to form products. And this reaction is going to stop or is going to finish once all the reactant or one of the reactant has disappeared. So this is why if I wanted to represent the irreversible reactions in a graphic way, like that one, so this is going to be the time, and this is going to be the concentration of my reactant. At time 0, the reactant will be at maximum, and then with the time they're going to break down until they become 0. While the product, they're going to be following a different pattern. At time 0, the product will be 0, and then with the time they're going to start to increase, and then they reach a fixed amount. The second type of reactions are the reversible chemical reaction, and this type of reaction somehow they're a bit new for you. You might did some bits about this in the GCC. And one of the examples that we can look at is the manufacture of the ammonia. So if you look at this compound ammonia, how can we make ammonia? We make ammonia by reacting nitrogen with hydrogen, but this reaction is a reversible reaction. So we need to balance this one. I'm going to multiply here by 2, multiply here by 3. This is gaseous state, this is gas, and this is gaseous state as well. So this is a reversible reaction. You're going to tell me how this is different from the previous one. I'm going to tell you that this is different because first the nitrogen is going to start reacting with the hydrogen to form the ammonia, and then this is going to keep going until at certain point what we're going to notice that we do not produce any more ammonia, and the amount of the ammonia doesn't increase, is not increasing anymore. And this actually telling me as well that from this arrow that we have two opposing reactions. We have a reaction going in this direction, and we have a reaction going in the opposite direction. So the nitrogen and the hydrogen molecules are combining together to form ammonia, but at the same time the ammonia molecules are breaking down to form again the hydrogen and the nitrogen. When the two rates, the rate of the forward reaction and the rate of the backward reaction, become equal, in this case we're going to say that we've reached something called the dynamic equilibrium. So we have some convention that we're gonna need to stick from now on when we look at chemical reaction. What these convention that we're gonna be looking at. So these are the conventions. So when you have a reaction, and this reaction is represented by a single arrow, this chemically mean that this reaction is a reversible reaction, which means that this reaction is going to be always going in this direction. So the reactant will be consumed to form a product, and the reaction stops when one or both of the reactant disappears or get consumed in the reaction. If I have a reaction and I've noticed I have this half doubled arrow, so that telling me that this reaction is a reversible reaction. And unfortunately, most of the commercial reaction or reaction that involve the production of commercial product are of this type, are of the reversible reaction. So for the A-level specification, we need to really understand and we need to define what is meant by the dynamic equilibrium. Okay, so this is how you're gonna define the dynamic equilibrium if you've been asked to define it. Okay, so again, this is a reversible reaction. It has two reactions. The forward reaction, the SO2 is combining with the oxygen to form the SO3. And the backward reaction, the SO3 is breaking back to SO2 and oxygen. Okay. How can we tell we've reached, or how can we tell that we have a dynamic equilibrium, or the equilibrium is reached? Okay, so we need to remember as well that to have an equilibrium we need to have some certain conditions. What are these conditions? To have an equilibrium, you need to be working in a closed system. By closed system, that means you're running the reaction in a closed container. So you can't have a dynamic reaction or a reversible reaction in an open system. In a reaction where the vessel or the container that you're running the reaction is open to the atmosphere. It needs to be in a closed container. Okay, so this is important. So this is the first criteria when we talk about dynamic equilibrium. So equilibrium can only be established in a closed system. By closed system, we means that there's no other chemicals that can get into reaction mixture, or any chemical is leaving the reaction mixture. Because if this happens, you're gonna break the chemical equilibrium. Okay, the equilibrium can be reached from both directions. So I can reach equilibrium from this direction or from this direction. What I mean by this, I mean that if you added SO2 to oxygen, they will react together to form SO3, and then the reaction is going to stop at after a specific time. But if you start the reaction with just SO3, the SO3 as well is going to break down to oxygen and SO2, and then the reaction is going to stop once you've reached a certain amount or a certain ratio between the reactant and the product. Equilibrium is a dynamic state, doesn't mean dynamic state, means that the reaction in both directions must be in the same. What I mean by this, we mean the reaction doesn't stop. If you have a reversible reaction or a reaction equilibrium, the reaction doesn't stop. You may see that you're not producing any more product. Yes, you're not going to produce any more product, but the reaction hasn't stopped. What is happening? It's the rate of the forward reaction is equal to the rate of the backward reaction. So the reaction doesn't stop. You're not noticing any difference in the amount of the reactant or the amount of the product. This is because the rate of the two reactions are the same, but they're going in the opposite direction. Okay. The last condition you need to remember that is dynamic equilibrium is going to be only achieved or stable under fixed conditions. But if you change any of these conditions, you're going to disrupt the equilibrium, and then you're going to see that some of your reactant is combining to form more product, or some of the product they are broken down to form more reactant. And this is one of the conditions, some of the stuff that we're going to be studying is how these parameters, the temperature, the pressure, and the concentration is going to affect the dynamic equilibrium. Okay, so if you have a reaction and this reaction has reached equilibrium, what are the factors going to affect the equilibrium? So these are the three factors that are going to affect the equilibrium. If you change the concentration of the reactant or the product, if you change the temperature or the pressure, if you change the pressure, and if you changed the temperature. Let's just, before we go and do a bit more on this, let's just give you some easy concepts to think about. So I'm gonna again focus on this compound, the ammonia. Okay, and the reason we focus on the ammonia, I did mention that several times now, is ammonia is one of the starting material we need to manufacture fertilizers, and fertilizers are very important for the growing crops and other plants. So we need a huge amount of ammonia, and ammonia is manufactured commercially using a process called the Haber process. And this is one of the processes you're going to be studying as well on the A-level. So in this process, how we manufacture ammonia, we bring a container or a cylinder that contains nitrogen. Then we have a container or a cylinder that contains hydrogen. And then we feed these two into a big container. So both of them are going to be fed here. And this container, they pass over an iron catalyst. So there's an iron catalyst here, where they pass over here. And then we heat this up. Okay, what happened? The nitrogen is gonna start to combine with the hydrogen to form ammonia. And you're gonna keep forming ammonia, forming ammonia, forming ammonia, and then suddenly you notice that the amount of the ammonia is not increasing anymore. So in this container, what you're gonna notice, that, for example, you started with 100 molecules of ammonia, 100 molecules of the hydrogen. You left that for 1, 2, 3 hours, and then suddenly what you notice that reaction had stopped, and you formed around like 30 ammonia, and this amount is not increasing anymore. So when the amount or the concentration of the reactant and the product, they're not increasing anymore, at this state, at this condition, this is when we say the reaction has reached equilibrium. We can represent this one graphically. If you have a relation between the time and the nitrogen you started with. So I started with a huge amount of ammonia here at time 0. And then with the time, the nitrogen amount keep decreasing, and then suddenly it's gonna plateau like this. So you've noticed here that the amount of nitrogen has not been dropped to zero, isn't it? So we didn't consume all the nitrogen. And this is one of the ways how we can tell that you have a reversible reaction, or you have an equilibrium, is that the reactant has not reached zero. Because if that reaction was a irreversible reaction, we'd expect the nitrogen to drop to zero like that. But this isn't the case. Okay. We can as well plot the ammonia. The ammonia gonna produce, it's gonna follow a pattern like that, but it's gonna reach the same plateau at the same time. So this is the time taken to reach equilibrium. So at the same time the reactant has reached plateau, the product as well reached at the same time. So when this has happened, that means we've reached the dynamic equilibrium. So what exactly happening here at this stage? At this stage, the rate at which the nitrogen reacting with hydrogen to form ammonia, this is happening exactly at the same rate at which the ammonia is broken down again to hydrogen and nitrogen. And so this is why we're not seeing any difference in the concentration. So, but again, we're saying that the reaction hasn't stopped. This is why we're using the word dynamic, is to tell you, yes, the concentration of the reactant and the product are not changing, isn't it? But there's still a reaction taking place. Again, when the rate of the forward reaction equals the rate of the reverse or the backward reaction, this is where we have what we reach the dynamic equilibrium. So I have a system now, and this system at equilibrium. What happens if I vary the conditions? What conditions are going to affect this equilibrium now? Temperature is going to affect the equilibrium. The concentration of the reactant and product are going to affect the equilibrium, and as well the pressure as well is going to affect my equilibrium. When I say it's going to affect the equilibrium, I mean that if you vary any of these condition after the system has reached the equilibrium, what's going to happen? This reaction may move forward or move backward, because you vary the condition at which this reaction has reached equilibrium. Okay. So again, let's look very quickly at some of the graphical representation that we have here. I'll just show something here about this graph. So this is another reaction. So this is the nitrogen dioxide, N2O4. If you have some of this nitrogen and you put it in a container, with the time it's gonna break down to form the NO2. So this is why you can see the N2O4 started, you put in a container and you close the container. With the time, the NO2 is gonna decrease, keep decreasing, keep decreasing, and suddenly it's gonna reach a plateau value. At the same rate, we're gonna find that the NO2 is being formed, again increasing, and then suddenly you're gonna reach what? A plateau as well. So at this time, this is where the equilibrium has occurred. Again, I keep repeating this. Equilibrium happens here because the rate at which the NO2 is breaking down to form NO2 happening at the same rate as the NO2 recombining to form the N2O4. So let's say you've reached this. This happened at temperature that equal 25 C, 25 degrees C, and at specific pressure 100 kilopascal, and at a concentration of 1 mole per dm minus 3. If you came and you vary any of these parameters, this equilibrium will be disrupted. By disrupted, we mean that this reaction might favor to go on this side or favor to go on this side to re-establish the equilibrium again. So this is why in this year we're studying something called the Le Chatelier principle. The Chatelier principle, this is a French scientist. Le Chatelier stated that if you have a reaction and this reaction has reached an equilibrium, so this is the first condition. We have a reaction and this reaction has been already under equilibrium. If you vary any of these conditions, if you vary the concentration, you vary the pressure, or you vary the temperature, what's going to happen? The system that is already in equilibrium is going to be disrupted, and he's going to respond to this disruption by trying to re-establish the dynamic equilibrium state again. Okay, so the way you can state the Chatelier principle, there is many ways of stating that one. This is one form you can use to state the Le Chatelier principle, but apart from the statement itself, you need to understand what we're doing here. Okay, we're saying you have a system at equilibrium, and some external factor like concentration, pressure, or temperature has been changed, and because of that the equilibrium state has been disrupted, and the system is going to respond by re-establishing the equilibrium again. Okay, what are these factors going to affect the equilibrium? The first factor is going to be changing the concentration. Okay, so here's an example. I have a reaction, a reversible reaction, where I react hydrogen and iodine to form hydrogen iodide. Okay, so you have a container, something like that. I've added here hydrogen, and I've added iodine, and I've closed this container. What's going to happen? Hydrogen is going to react with the iodine to form hydrogen iodide. But unfortunately, this reaction isn't a reversible reaction. This reaction is reversible reaction. So that means some of the hydrogen and the iodine, they're going to react together to form hydrogen, and then the reaction is going to stop at specific time. Okay, when the reaction is going to stop? The reaction is going to stop when the ratio between the reactant and the product, so when you reach a specific ratio, when the ratio between the product and reactant reach specific value, and this value we're gonna study later is called the Kc. So every irreversible reaction is gonna keep going until it reaches this ratio, and this ratio is not fixed. It's specific for each chemical reaction. Okay, so that means the hydrogen and the iodine, they're gonna keep reacting with the to form hydrogen iodide until the amount of the product divided by the reactant reach value. Let's say, for example, in this case, is gonna reach a value of, let's say, 0.1, until it reaches a ratio called what? 0.1. So I have a system now, and the system reached equilibrium, and the ratio between the product and reactant has become 0.1. What happened if I came and if I opened my container like that, and I came here and I added more what? More hydrogen, and then I've closed the system again. What's going to happen to this ratio? This ratio is going to get bigger or lower or smaller or larger, or anyone is going to volunteer to tell me what's going to happen now to this ratio? Guys, no one? So I added hydrogen here. So this means the amount of the reactant has increased, isn't it? The amount of product still the same. So this means this ratio is gonna be less than what? Less than the 0.1, isn't it? So what's gonna happen? The system is gonna need to respond back, isn't it? It's gonna need to respond back to return this ratio back to what? To 0.1. How it's gonna respond to make it 0.1 again? Is by increasing the amount of the product and decreasing the amount of the reactant.
I think you muted yourself.
Sorry guys.
It's okay.
So we're saying at any equilibrium, the ratio between the reaction is gonna keep going until you reach a certain ratio. Okay, we said for this case, for example, this ratio is 0.1. So what's gonna happen if I added more hydrogen to this system? If I added more hydrogen to this system, that means I'm increasing the amount of what? Of the reactant. And because of increasing the amount of the reactant, this ratio isn't gonna be any more 0.1. It's gonna be what? Less than what? Less than 0.1, because I've increased the bottom, isn't it? So the system is gonna respond back. It's gonna say no, I want it to return back to the 0.1 again. So how they gonna return back to 0.1 again? They're gonna do this by reacting together again to produce more what? More product. So I'm gonna increase the B, I'm gonna decrease the R, and reestablish this again to 0.1. So for any equilibrium, this is the target of the system. The system wanna to reach specific ratio, and this ratio is specific for each reaction. We're gonna study this later, which we're gonna call it the Kc. I'm just trying to get this in your head. Remember, please, that in equilibrium reaction, the reaction is gonna keep going until it reaches a specific what? A specific ratio. If the reaction has reached specific ratio now and is happy and at equilibrium, if you came now and you played in the system by any way, the system is gonna respond because he wanted to get back to this dynamic state that he was in earlier. Okay, so this is why I really don't want you to memorize this stuff. I really want you to understand that. So here's the example we're showing. I have a system at this equilibrium. What happened if I increase the concentration? What happened if I added hydrogen to this system? If you added hydrogen to this system, that means I'm increasing the concentration of the hydrogen. And because of that, the equilibrium has to shift to what? To the product side. So by shifting, we means that the rate of the reaction is going to be more faster on the right hand side, because he want to produce more of the product to return back to the same what? To the same ratio. Okay. So if I added hydrogen to the equilibrium will shift to the product side, and that means, and the reason for this one is to reduce the concentration of the hydrogen to counteract the change that you made, and the mixture will become less purple. The idea about the color is these compounds here, the reactant and the product, are colored, isn't it? So if the amount of the HI is larger than the amount of the reactant, the mixture will be having this color more than this color. So when you start the reaction, your container is gonna look purple. So this is my container. So the container most likely is gonna have what? A purple color, because you have this as your reactant. But with the time, the amount of the iodine is gonna get consumed, and you're gonna produce a colorless solution, isn't it? So this is why the mixture will become colorless. Okay. What happened if I removed some of the iodine? So if you removed some of the iodine, let's check the ratio again. I'm dividing product by reactant. I'm removing iodine, so I'm making this one small. So if you're making this small, isn't it? The product has to convert into what? Into reactant. Again, to reach the same ratio. So this is why if I removed iodine from the system, isn't it? This will decrease the concentration of the iodine. Equilibrium is gonna run more to the left hand side to produce more reactant, isn't it? So they can counteracting the change that you already made. Remember, in any equilibrium questions, you need to mention this bit. The equilibrium is gonna move to oppose the effect. It is the change in concentration, is it the temperature or the pressure? The second parameter is gonna affect the equilibrium. It's gonna be if you vary the pressure. So if you're working with gaseous molecule, isn't it? Remember that the pressure is going to affect only gaseous molecule. This is, you need to take note of this. Pressure affects only what? Gases. Okay, so if you have a reaction, this reaction have a solid or liquids, the pressure does not affect the liquids or the solids. The rules we're going to be learning here is that if you increase the pressure, the reaction will be shifted to the side with the fewer number of moles. And we're talking about the gaseous mole. Okay, so let's look at this example here. I have this reaction and this reaction at equilibrium. Okay, what's going to happen if I increase the temperature on this reaction? So increase the pressure. So what I'm going to do, I'm going to look at the left hand side and see how many gaseous mole I have here. I have what? I have one gaseous mole on the left hand side, and then on the other side, on the right hand side, I have two gaseous mole. So if I increase the pressure, this reaction will be shifted to the side with the fewer number of gaseous moles. It's going to shift to the left hand side. Okay. So we have here some interactive thing I want to show you about this specific example. So this is the example that we've been looking at. If I have, just give me a second, I'm gonna swap my presenter view. Okay, so this is the example that we're talking about. We have this gas, the N2O4, and we put this, or we started with the NO2 in this syringe. So this is the syringe. I've closed it from one side, and I did put some of the NO2 in this compound. Okay, and this reaction is happening now and has reached equilibrium now. Okay, what's going to happen if I increase the pressure? Okay, remember that the NO2 has this brown color and the N2O4 has a colorless color. So if I increase the pressure, that means I'm pushing this plunger to a bit further. So because you're increasing the pressure, this equilibrium is going to shift towards the left. Why is going to shift towards the left? Because the left hand side you have a fewer gaseous molecules. Okay. If you decrease the pressure, by decreasing the pressure, I'm saying we pulling this to the left hand side, isn't it? This is going to have the opposite effect. It's going to move to the side with the higher number of gaseous molecule, and the color of the mixture is going to become a bit darker. Okay, so it's not recommended actually to memorize two opposing rules. So this is why we're going to be sticking only to one. We're going to be sticking only to one rule, isn't it? Just I need to remember when I increase the pressure, the equilibrium will be always shifted to the side with the fewer number of gaseous molecule. Okay, and then you can build on this rule. So don't please remember two opposing rules. Just remember one rule, and then if you've been asked the opposite, build on this one. Otherwise, you're gonna get confused. Okay, so the rule we're gonna be learning is that increasing the pressure will shift the equilibrium to the side with what? With the fewer number of gaseous molecule. Okay, the last reaction or last factor we're going to be looking at today, it's going to be the effect of the temperature. And to understand how the temperature is going to affect the equilibrium, I need to know the enthalpy change of the reaction itself. I cannot judge about how temperature is going to affect the equilibrium without knowing the enthalpy change of the reaction. So I have a reaction here, and they're being given delta H, and delta H has a positive sign, and positive sign mean that this reaction is endothermic reaction. But remember that we have two reactions going here, isn't it? We have the forward reaction and we have the backward reaction. So this delta H belongs to which reaction? This delta H belongs to the forward reaction. Okay. The backward reaction is going to have exactly the same delta H, but in the opposite sign. So this reaction here is going to have delta H of positive 58. The backward reaction is going to have the same delta H but with a negative sign. So the forward reaction in this case is endothermic, and the backward reaction is exothermic. Again, we're going to be learning one rule when it comes to the temperature. The rule we're going to be learning is that increasing temperature will favor the endothermic direction. Increasing the temperature will favor the endothermic direction. So let's apply this rule to this reaction. Being given the exam this equation and being asked to predict what's going to happen to this chemical equilibrium with this reaction if you increased what? If you increase the temperature. What I need to know, I just need to check where is my endothermic reaction. My endothermic reaction is going to be on this direction because in this direction the sign is positive. So that means increasing the temperature will shift the reaction to the endothermic what? Endothermic direction. So that means you're going to produce more what? More product. Okay? And vice versa. If you've been asked about the decreasing temperature, work the opposite rule. But as I said to you, please don't memorize two opposing rules. Otherwise, you're going to get confused. Just memorize one of them. The last parameter is how the catalyst will affect the equilibrium. So the effect on the catalyst does not affect the position of the equilibrium. So if you use the catalyst or you didn't use the catalyst, this doesn't make any difference where is the position of the equilibrium is gonna take place. So it doesn't favor any directions. Why this is the case? It's because the catalyst will increase the rate of the forward and the reverse reaction by the same amount. Okay, the impact of the using a catalyst is gonna, if you use the catalyst, what's gonna happen? The time needed for reaching equilibrium is going to decrease. So if you have a reaction and this reaction is reversible, might take hours and hours to reach equilibrium without catalyst. But if you use the catalyst, the time to reach equilibrium is going to decrease significantly. And again, just please remember this rule that the catalyst does not affect the position of the equilibrium. Because it increases and decreases, because it increases the rate of the forward reaction and the backward reaction by the same what? By the same amount. Okay. So we're gonna stop here for today, and then next week we're gonna be looking at the calculations, how we're gonna define the chemical equilibrium constant, the KCE, and how we're gonna be doing some calculation with this one as well.